Hello. This video is on Chapter 10, Analysis of Variance, the subject of one of the topics for this week, Chapter 10. And thought we'd go through the rationale for analysis of variance and compare how it is with a couple of other techniques we're learning over this week and next week. Cross-tabulations and analyses and correlations. And let's do that first. We had done this once before, I think, when we were doing cross-tabulations, and we'll do it again when I do a video on correlation on Tuesday of next week. This is November the 21st, Thursday. You recall that we are now, as of Chapter 10, even though we went from crosstabs 11 to 14 for the cross-tabulated homework, then and cross-tabulations, we step back now, go back a chapter to do analyses of variance, and then on Tuesday, today, this week, and on Tuesday we'll be working on correlations, and I'll do a correlation video and the other pieces that are out of 15 in a video on Tuesday of next week before Thanksgiving. I think that's the 26th or something like that. All right, so where we are, once we get to, even though the text says Chapter 11, bivariate explanatory analysis or bivariate analysis, really analysis of variance is bivariate analysis and fits well with these three types and techniques that we're talking about, cross-tabulations, analysis of variance, and correlation, where we have a bivariate explanatory analysis. And what we're talking about here, this is the equation, basic equation, y equals x. Our dependent variable is y. What does the variation of y depend on? We're going back to chapters 3 and all of that, the variations in chapter 4, all of the things that we've been doing, just continue to follow forward with us. So we're looking at why, say if this were income, why does income vary? And we might hypothesize that it has to do with education. That is, education varies, income varies. So in other words, as education goes up, income goes up. And so when we're looking at bivariate, that's two variables, of course, analysis, we're looking at it from the standpoint of explanatory or explaining. In other words, we want to be able to say how much of that variation in y is explained by x. How much of the variation in income is explained by, in this case, education. And then in this matrix that I set up for you to think about, we have the dependent variable and independent variable. So when we say dependent, we say depends. What does the y, the variation in y, depend on? What is it responding to? And so then we hypothesize that it's education, that it depends on education. Now remember last time, I think we talked about in the video why we call this independent, because we might have an x1 and an x2 and an x3 or more on the right hand side of the equation, so that we could look at x1's relationship with y independently of x2's relationship with y, independently of x3's relationship with y, and so on. So that's this thing having to do with independent when you think of independent of what. And it's not like independence is in the crosstabs, that they are independent of one another, although that's a piece of the null hypothesis that we'll talk about here in a minute. But this is a different kind of independence. Sometimes statisticians use the same words, or statistics does the same words, and they just mean something different, which is not helpful, right? So anyway, here we've got use a cross-tabulation, that's chapters 11 through 14, when your dependent variable is categorical and your independent variable is categorical. For example, if do you approve capital punishment, yes or no? That's clearly a nominal variable. That's the dependent variable. Why are we not all yeses or all no's? And we might have on the right-hand side gender, male and female. And so we might look at, is there a larger percentage of women favoring capital punishment relative to men, or the reverse? So that we can look at that in a cross-tabulated table, and they're both categorical variables. And in both of those are nominal, but it could be an ordinal variable. These could be ordinal variables as well. The point is they're categorical. And then in analysis of variance for chapter 10, we have a continuous dependent variable, y, and a categorical independent variable, x. let's just say that we're using income and education, but here let's say we got income as a continuous variable, and we're using gender as a way of explaining the variation. Why is it we don't all have the same level of income? Well, of course, there are a number of explanations for that, but one that's in social sciences that's been prominent over the last generation or two is some of the variation has to do with gender, in the sense that in the old days, and not so much anymore, but maybe still a little bit women might earn less money even with the same level of education and experience. Not the right sort of way to be, but nonetheless it has been true in our society in the past, and still is probably a little bit. So then what this would happen then, we'd have male and female as a categorical variable, and then an analysis of variance will take that income continuous variable and look at the mean for the females and the mean for the males, and then test whether there's a significant difference between those two groups. And that's the analysis of variance, the analysis of the variation of income across the two categories of gender, male and female. That's the analysis of variance, or analysis of variation if you prefer. And then what we'll be talking about on through Tuesday of next week is correlation. That's where they're both continuous, and that's more like the model we were talking about up here. Why is income varying? Why don't we all have the same amount of income? And we might hypothesize because we don't all have the same amount of education. And we might do a survey to test this and find that people with 9 years of education have a certain level of income. People with 12 years of education have a certain level, but a little higher on average. And people with 14 have a little higher still. So then we might see that as education goes up, income also goes up. But we'll talk more about that in the next week and in the video that I'll do for you. Today we're in analysis of variance. Now, over here, if you can read my writing, this is chapter 10 is what that says. We're talking about analysis of variance. In a more popular way, it's just simply called ANOVA. Like this is cross-tab. They don't have any Corey, or Corley, or anything like that for correlation. Just name it correlation. But here, cross-tabulations we call in the short term cross-tabs, and analysis of variance we call an ANOVA. All right. So just like everything that we're doing has in that pathway population of parameter. We can't go there because it's too expensive. So we draw down a sample, and we make sure that it's random and of sufficient size. And so when we get a statistic, in this case an ANOVA, we can infer that had we done an ANOVA from the population to the parameter, we would have had basically the same ANOVA, more or less, give or take a little bit, but basically the same. We've got a sample of sufficient size and it's random, so the dynamic of understanding ANOVA within the statistic, or within the sample, is very similar to the dynamic we would have encountered had we done the population, an ANOVA off the population. So we feel good about that, right? So we're still doing that kind of thing. So there's a null and a research hypothesis, just like there was with crosstabs, just like there were in chapters 8 and 9, and just like there will be as we get into chapter 15. There is a null and a research hypothesis. Now, when we're talking about ANOVA, that means that the categorical variable probably has at least two categories, let's say, like we talked about here, male and female. So we might just have the, like here, if it were income, that the average for males and the average for females, the null would say that even if we see a difference, it's a numerical difference and it's trivial. Remember, we've been through this concept before. Disregarding these two out here, this would be male and female, and the null hypothesis would be that income, whatever we see as a numerical difference, is only trivial, not statistically significant. The research hypothesis would say just the opposite of that. It would say that what we see in these values between the two, the average for males and average for females, is statistically significantly different. And we would go through that. Now, where we have a chi-square statistic here, we have an F statistic here. Basically, the larger the chi-square, the more significant in a way. The larger the F the more significant in a way in terms of the relationship between the two variables, and we'll walk our way through that here in a minute. So here we've got null equals mu1 equals mu2 equals mu3 equals however many mu's there might be in the categories. And the research would say, maybe draw a line diagonal through that saying mu is not equal to mu2 is not equal to mu3, and all that would be the research hypothesis. Now I've got an illustration up here because I want to, about infant mortality rate, that's what the IMR stands for, where X has 4 categories and each category is a different neighborhood. I want to speak to analysis of variance as kind of a particularly interesting and useful statistic for the social sciences, and particularly for sociology. The sociological perspective, the sociological perspective is the contextual influences on human behavior. So that if you got one family, you got 3 families, and you see a variation in children coming out of those families and on some dimension, behavior, is there a way of explaining to some extent the variation in that behavior by the context of family? Are the dynamics of the 3 families sufficiently different to account for the variation in behavior on the part of the children coming from those 3 families? Or it could be most anything, It could even be race and ethnicity. Is the context of race an important determinant of behavior? For example, if we're on approval of capital punishment, or if we had some kind of scale, let's say, where this is a continuous scale on capital punishment on a 0 to 10 scale, would we see the average for African Americans different from the average for Hispanics, different from the average of non-Hispanic whites? Context of ethnicity. But here I wanted to speak to something that is more specific to the kind of work I do out in the community and why I use analysis of variance conceptually and often statistically. And that is, we have infant mortality rates, and I'll speak of San Antonio here. We have infant mortality rates that vary by neighborhoods. One side of town has one rate of infant mortality, the other side has a different rate, and the third and fourth have different rates still. And so when we characterize infant mortality rate as a continuous variable, infant mortality, by the way, is the number of children who die in the first 11 months of life, divided by, that's the numerator, divided by the number of live births in that year. It's usually by a year because it's a rate. So we'd say in 2012, the infant mortality rate in San Antonio, let's just say, is 10. And that would have been determined by dividing all of the babies who died before their 12th birth, their first year of life, by the numbers of live births in 2012 in the denominator, and then multiply that times 1,000 or something, would have given us the IMR, the infant mortality rate. So in community health, we're concerned about the geographic variation. Why is it that some neighborhoods have higher and some don't, and so than others? And so we look at analysis of variance across categories of neighborhoods. So the null hypothesis, of course, would say that all 4 of these have the same rate. Even though we see that they're different, it would say that the differences are only trivial. But once we do the analysis of variance, we might find that 4 is, let's say that we're looking for, let's say that Healthy People 2010 is looking for an IMR where IMR equals 8 per 1,000, and that's the goal that we're after. This one we can see from the analysis that we've done. This one's at 7, this one's at 12, this one's at 9, and this one's at 16. And so then what we want to do, we already see that there's a much higher rate here than there is here. This is a lower one than that, so that neighborhood's doing pretty well. So what we begin to think about is, can we show that this is statistically significantly different? That it's not just a trivial difference in neighborhood 4 from any of the rest, but statistically significantly different. And the reason why we want to determine that it's statistically significantly different, because if we decide from the statistics that that is so, then we can work with Metro Health Department and the mayor's office and community-based organizations and whatever else to bring in resources into this neighborhood to help families and mothers in particular, help them improve their context such that children will survive in that neighborhood at a higher rate than they are now. Or in other words, that infant mortality will drop down to something closer to over here and maybe even below 8. So this becomes a diagnostic. If we can show statistically different to this significant difference, then that warrants, that's evidence for a neighborhood intervention that will help the families in that neighborhood have better birth outcomes. And so that's why I say I do community health practice, and many of you out there will be working for community-based organizations, or perhaps you already are, or you'll be using your sociology degree or whatever degree you're going to do in nursing or whatever it is. You might likely be in some kind of a community setting where you're looking at variations in health of some sort, and you're trying to determine whether what you see from one side of the neighborhood or one side of the city to the other is statistically significant. And if it's so, then that gives you some evidence for doing interventions. And that's why I stress analysis of variance is particularly useful for social sciences, particularly sociology, because the sociological perspective is the contextual influence on human behavior. In this sense, the contextual influence defined by neighborhood, and the behavior here we could say is the child mortality, but it may well be that there's the behaviors related to the mother, something going on in the neighborhood that creates stress on the mother, so that the nutrition of the child in utero is not quite as good, and so the child is born but maybe weaker than it might have been if the mother was living in a neighborhood that's with much lower stress. So just wanted to point that out. Okay, now I'm going to open up the text here for a minute. I'm on chapter 10, and you can see there it defines ANOVA on page 234. The logic of the analysis of variance, it speaks to the mu there, the null, mu1, mu2, mu3. We're in a null. It is called the hypothesis testing 3, just like the hypothesis testings we've been in previously. And they've got an example there, support for capital punishment in table 10.1. But let's look at table 10.2. So when you look at table 10.2, you can see that they're doing this based on religious affiliation. And you see Protestants are 14-something, Catholics are 11-something, Jews are 5-something, and none is 8-something, and others 7-something. So what we're looking for there is how much is that different, these two, than the other. And I might want to point out here that one of the things that is important when we look at this in the analysis of variance is that in the analysis of variance we recognize that there's variation of mortality within a neighborhood. In other words, if this were 6, then that doesn't mean that all the children in the neighborhood are dying as infants. So there's variation here. There's variation here. I don't remember the numbers I had. So there's variation. Not every child born in these neighborhoods is dying before the first year of life. So we know there's variation within the neighborhoods. We know that by looking at the numbers. What is interesting to us as social scientists and sociologists in particular is the variation between. If we can show that this is statistically significantly different, the variation between neighborhoods, then we've got a good logic and a good evidence for intervention in terms of the illustration I was giving a minute ago. So if you'll look over on the next page, you'll see, well, on page 237 on formula 10.2, we're not going to do the mathematical part of this, as you can just spend some time and look at that and see that it's quite a lot of work to do by hand. So that's where we're focusing at this point, getting the transition to thinking about statistical packages and getting results and interpreting those, making that transition into it. If you look at formula 10.1, you can see they call this the sums of squares, and really what we're talking about there, the total amount of variation in infant mortality, let's say, is equal to the sum of the variation within each group plus the sum of variation between each group. And you can see there SST equals SSB plus SSW. So the concept there is the total, and what analysis does, it partitions all of the total variation into that amount that varies within each category of the independent variable and the amount of variation that is between between the categories. It's a very important distinction. You can take you over to, for example, formula 10.9 on page 238. Now we're not going to do the mathematics of this, but if you look at this, you'll see formula 10.9, F equals the amount of variation between divided by the amount of variation within. So the basic idea of that is if we get something in that F statistic that's larger than 1, that means that the amount of variation between is more than the amount of variation within. And if the amount of variation is more between, then we have a logic for contextual influences if we're thinking as social scientists. So that F statistic is a conceptual image right there of what this can do for us in terms of looking at the distinctions between contexts and their possible influence on the outcome of interest or the dependent variable of interest. Now, you're not going to have to do the math or anything like that. I just want you to be aware of formula 10.1, the concept of that. The total amount of variation is partitioned into that that's within and that's between. And then formula 10.1 is the concept of the F statistic, and where you put the between variation in the numerator, the within in the denominator, and divide the within into the between. And if you get something larger than 1, then you know that there's more variation in this outcome variable being explained by between than there is within. And from the standpoint of social sciences, that's a research hypothesis we'd like to get, I guess, if we want to develop an intervention. So the larger, again, the larger the value of the between, the larger the F statistic. And that goes back to the idea I was saying a little while ago. As the F statistic goes up, basically you get this concept, as it goes up, there's a greater amount of significance between the contexts represented by the categories on the right-hand side of the equation. Okay, now, if, for example, we can just look at, I think he's got, well, all these are several pages long. You can spend some time looking at the applications to get an idea about what it would constitute or what you would have to do if you were to do one of these problems, but the computer, thankfully, is going to do it for you. Your job will be to interpret it. I do want to point out to you formula 10.5 and 10.6, much like when we were in the t-distributions back chapter 2 ago, when we were in chapter 8 and 9, and the population, or I should say the sample size, was less than 100, we had to use degrees of freedom as a way to arrive at a critical value. So when we're talking about an F here, you're going to be presented by the software an F observed, and then you're going to go using the degrees of freedom back here to this is a different text, so I don't have my appendix marked here, but to Appendix D in the back of the book, where it says distribution of F at 0.05. Probability equals 0.05. It doesn't have a page, but you go to Appendix D, distribution of F, probability equals 0.05. That will be the table that you will find your critical value. So here then, we would look at the degrees of freedom within. It's the sample size, that's N, minus K, which is the number of categories. So if this were 100, if we had 100 cases of infant mortality and we had 4 categories, then it would be 100 minus 4, and that would be 96. That would be that degree of freedom within. And then if you look at formula 10.6, here we've got 4 categories. Its degrees of freedom between is K minus 1. So the degree of freedom between would be 4, minus 1 would be 3. And that's the way basically how you would do it. You count up the number of categories in your independent variable and subtract 1 from that. You take a look at what your sample size is, and you subtract from that the numbers of categories in your independent variable on the right-hand side of the equation. And that's how you do that. All right, let's use an illustration. I've sent you out already a couple of, maybe 4, analyses of variance. I don't remember how many it was. Demonstrations, and this is one of them. This one is Respondents' Socioeconomic Index by respondents. I'm going to move up a little closer, even though we might lose. Let me see if I can turn this up a little bit. Yeah. Demonstration ANOVA where respondents' socioeconomic index by respondents' race and ethnicity, chapter 10. I don't know if you can see this, but that's the one I want you to pick out of the ones that I sent you, so that we're following on the same one. And everything that, all the others that I sent you for demonstrations, exactly the same process. All right. Now the way that you would think about this, respondents, socioeconomic index by respondents' race and ethnicity. The way these things are set up, and the way I do it, and the way ordinarily it would be set up, anything to the left of the by in a title like that is the dependent variable. Why is the socioeconomic index varying? Now the index is like a socioeconomic status. It's comprised of continuous variables of education, occupation, and income put together and into an index. Probably some other things as well. And then on the right-hand side is respondents' race and ethnicity. So what we're looking at here is how does the SEI vary across the several or however many categories of race and ethnicity we have in this thing. So we look under instructions, dependent variable, economic index, independent variable, respondent's race, the null hypothesis, null mu equals 1 equals 2 equals 3 equals 4. In other words, this index is continuous. Each one of these categories of race and ethnicity has its unique mean. Now, the thing you could say is that the easiest way to say it is that race and ethnicity and a socioeconomic index are independent of one another, much like we did before in crosstabs. They're independent of one another. In other words, neither one nor the other influences the other. There's no relationship such that one is influencing the other. They're independent. That's the easiest way to say what the null hypothesis would be. But on the other hand, the research hypothesis would say that it does influence race and ethnicity. There is a variation, a statistically significant variation across the categories of race and ethnicity of SEI. All right, so here we have the degrees of freedom. And we see we've got an alpha of 0.5. And that's, as I've said before, that's a pretty standard alpha. We're willing, remember we're in a probability model here where we're estimating what we would have found if we've gone from population to parameter. If we drew down the same sample of the same size, we might, we recognize there'd be some variation because the sample of the same size would be comprised of unique individuals. If it's a sample of 4,000, the next sample will be 4,000, but maybe 4,000 different individuals in the previous sample. So there's going to be some variation. So we do the alpha of 5 saying that 100, if we did 100 of these, 95 out of 100, we're willing to take an error chance of 5 to reject the null. So in other words, we'd have an alpha error of 5. That's a risk and of being wrong 5 times out of 100. And that's what the alpha is about, as we know. All right. So let's look at degrees of freedom between. Let's flip over to the table in the back on the next page. And you'll see that there are 3 categories of race and ethnicity. Non-Hispanic, white, African American, Hispanic. That means we have 3 categories. And so when we flip back over here and we say degrees of freedom between k minus 1, we do 3 minus 1, degrees of freedom equals 2. All right? And so then we look at degrees of freedom within is n minus k. We come down here to the total and it says 4,051, sizable sample size, eh? So then what we would do to get the degrees of freedom within is we would take 4,051 minus 3, and we would get 4,048, right? So you would do that math and put it right there. And then we'll go to Appendix D. So let's go to Appendix D. And distribution of F. And there you'll see the table is laid out, somewhat familiar. The top row, right up here at the very top, are your degrees of freedom between, all right? And the left-hand column going down are your degrees of freedom within, all right? So we said that the degrees of freedom between are 2, and so we go over 2 columns beyond that first column to 2, and then we go down that column until we come to 4,000 and whatever it was, 4,050 or whatever it was. And you'll notice in the left-hand side it goes down to 120, then it drops into infinity. This is very much like a t-distribution. once you get down there at a certain point, it begins to look like a z-distribution, all that kind of stuff. So what you do, just like you would in a t-distribution, you take the value that's closest to yours. So you come down and you just take the infinity value, because this is like 4050, and so you would move across to the right to the second row where you've got 2 degrees of freedom, and I get 2.99. That's what I get for the critical value if I did this correctly. Degrees of freedom are 2, and we're in the infinity level of the within. So that's 2.99. I'd come back to that first page, and in the critical value, I would put 2.99. And then, that's the F critical. Say that's the F critical. And then I would come back to here, and I would see that the F statistic here is 81.951. So then you decide, is that larger or smaller than your F critical? Looks larger to me. So then we would say the F observed is larger than the F critical. And what would you do if the F observed is larger than the F critical when it comes to rejecting or not the null hypothesis? Yes. What would you do? Yes, that's exactly what you would do. You would reject the null. Anytime, as we've already seen from Chapter 8, Chapter 9, Chapter 10, 11, all that kind of stuff, anytime the null hypothesis or the observed value, the observed chi, the observed whatever it is, the observed t, the observed z, are larger than any of those statistics critical, then you reject the null. If, for example, we had gotten a F that was 93, then it would have been larger than the F critical of 81, and we would have failed to reject the null. Okay, so there you got that. And that's how you would do your interpretation, making a decision and interpreting the results of the test. And then I ask you to do something to resurrect an old idea, and that is the confidence interval. We want to keep the confidence intervals in front of you. Relay the decision and explanation of the part of the descriptive table having to do with 95% confidence interval for the mean. So let's just, for example, go back and we look. And we look at the mean for non-Hispanic white, for example, is 51.385 right here. That's our point estimate. Our point estimate from the sample is that. And then you notice over here, there are 2 columns right in here. 95% confidence interval for mean. That means that if we were to do 100 samples of the same size, the means would vary 50.6 to 52.0. So there you've got a confidence interval, and that's exactly what you would say. For the point estimate for non-Hispanic whites is 51.385. If I were to do this sample, 100 samples of the same size, that non-Hispanic white mean would vary somewhere between 50.6 and 52.07, and do that for all 3 categories. Restate the confidence interval, and that's it. So, and that is the analysis of variance. So, anyway, thank you for your good work. Those of you, I send this, turn this into a YouTube, and this is principally for those of you that are in the online class, but I also send it to the face-to-face class. And the online class, the face-to-face class has finished the exam 3. The online class, you're doing exam 3 now, or at least you have it until, I think I said Sunday night, midnight. And you've got homework assignment already, and I'm still finishing out previous homework assignments. So I'll be coming in on Sunday and finishing all those out and sending them to you. I'm a little bit behind on that. But like I said in the email, the calculation part of those chapters covered by exam 3 are not important to the concept questions of chapter 3 or exam 3. So you can do the exam 3 based on concepts without having done the calculation. So please proceed with the exam. All right, thanks a lot. And Tuesday of next week, 26 I think, I'll do a video on chapter 15. There'll be 3 parts there: the scatter plot, the correlation, and the prediction, and regression. They're all in the same chapter. And so have a good weekend, and I'll talk to you next week.